picture, the blue line corresponds to our universe, three-dimensional universe. So our universe could be part of the brain, this green space, which has extra dimensions, along which standard model interactions can propagate. So these extra dimensions, if they exist, they should have a size 10 to the minus 16 centimeters. So this is a very small size. On the other hand, there could be extra dimensions which are transverse to the brain of the universe. So these extra dimensions correspond to the yellow space, and they interact with us only by the emission of closed strings. So only closed strings can propagate into these extra dimensions. And these closed strings describe gravity. So gravity is here, standard model interactions are there, and these dimensions along the yellow space can be much larger, as large as a millimeter, as a fraction of a millimeter. And so these are the, of course, experimental bounds, and one can use the same numbers as before to so the fact that gravity becomes as strong as the other interactions at the TV scale in this framework implies simply that the string scale is at the TV, so it's within the reach of the LHC. And for this to happen, one needs extra dimensions, gravitational dimensions, of the size of the volume approximately 10 to the 32 in the string in string units, and this 10 to the 32 accounts for the hierarchy and can be spread into the size of extra dimensions depending on the number of them. So this 10 to the 32, if there are two dimensions, each one must have a size 0.1 millimeter. If there are 6, then each one has a size 10 to the minus 15. So if this is a possibility, this gives a new framework that in principle is testable in LHC and other experiments. As I said, if there are extra dimensions with finite size, then at distances larger than the size of the extra dimensions, there is no effect. Gravity is as usual, dimensional. However, if one could perform experiments at shorter distances, shorter than the size of these extra dimensions, then the behavior of gravity would change. It would behave like it would see the extra dimensions. It would become like 3 plus n dimensional. And in particular, the Newton's law will change. The Newton's law will decrease with area, as we know. So in three dimensions, the force decreases like 1 of the area of 1 over r squared. While if there are n extra dimensions, the force will decrease as 1 over r to the 2 plus n. So for instance, if there are 2 extra dimensions, then the force will decrease 1 over r to the 4. And this would be should be observable for sizes, for distances less than about 0.1 millimeter, which is there where the experimental bounds exist. Of course, this is one way to detect the existence of such extra dimensions. Another way to do it is by observing the effects of strong gravity at the TV scale, where is the string scale, and where the gravity becomes strong. So let me describe briefly the effects of this scenario in accelerators. So the model-independent signal would be gravitational radiation from any process which is occurs on the brain where we live, And this gravitational radiation corresponds therefore to a graviton which is emitted, which we cannot observe, and therefore should give rise to missing energy, like the missing energy of dark matter particles, but different source due to the gravity emission. So present LHC bounds, due to the non-observation of such missing energy, imply that the scale of higher dimensional gravity should be bigger than 3 to 5 dB, depending exactly how many dimensions there are. Now there are several other accelerator signatures in addition to the effect of missing energy due to the graviton emission, which are of 3 types. One type of signatures has to do with the existence of large dimensions which have inverse TV size, 10 to the minus 16 centimeters, those that are seen by the gauge bosons, by the standard model interactions. The way to detect them is through the production of Kaluza-Klein excitations that I mentioned before. For instance, for the photon, the Z and other particles. So, for instance, these are, for instance, a possibility that the first excitation of the photon and the Z are produced and decays into leptons. Then one should see a resonance. This is way to detect. Now, the size of these extra dimensions vary between a few hundred GeV to 40 V, depending how matter is localized with respect to them. So there are essentially 2 possibilities. One possibility is that these Kaluza-Klein excitations, the extra particles, are produced directly. In this way, one has new resonances, new particles that one can see in a clear way, but then the bounds are strong. Or there is a possibility that these particles are produced by pairs because they are protected by symmetry, light and supersymmetry. In this case, the lightest Kaluza-Klein particle could be also a candidate of dark matter, and the bounds are weaker, about 500 GeV. Actually, this case experimentally looks very similar to supersymmetry. If one replaces supersymmetric partners by Kaluza-Klein particles. And it has been studied a lot in the literature. Another possible signal is to produce string excitations. So these are vibrations of the string, which have masses of the order of the string scale. And these vibrations have this mass formula. The mass square increases with a spin, with a maximal spin. So the most, as you increase the excitations, you increase the spin. And for instance, one should be able to see higher spin excitations of quark and gluons with strong interactions. For instance, spin 3½ excitations of quarks or spin 2 excitations of gluons that have been studied. And so this is characteristic signal. And the limits, the present experimental limits, is about to give direct bound of the string scale around 5 dB. And also another type of signal are extra U1s, so extra G primes, which are and the reason is that these extra gauge bosons, these extra which look like the photons or the Z, they have masses which are suppressed by an order of magnitude lower than the string scale. So even if the string scale is, let's say, beyond the reach of the LHC, still they could be produced the LHC. And they could be, they could indicate that there is a string scale there. So since my time is over, let me go into the end. I mean, perhaps I should say that I mentioned the experiments that test Newton's law at short distances. Actually, these experiments test in general new forces at short distances. The reason is that in the case, in general, in the bulk, which is the space of these extra dimensions, you would have, besides the graviton, also other particles that could meet, like scalars or gauge fields, that could mediate forces at short distances, and this could be tested. Could be, of course, they are model dependent, and the experimental analysis usually happens by parameterizing the extra forces as an addition to the Newtonian potential with two parameters. One is the wavelength of the new force, and the other is the strength of the new force relative to gravity. So this is the strength of the new force, and this is the wavelength of the new force. So gravity is here. So for instance, the Antoniadis experiment that I showed before corresponds to this point here, but the experimental analysis is a two-parameter plot. So if the extra force becomes weaker than gravity, then the bounds are weaker. If they become stronger, if they are stronger than gravity, of course the bounds are stronger. So there is all this region, which in principle there are various models that predict new forces at short distances, and these are currently explored by such experiments. So okay, these are pictures of various experiments. So arrive to the conclusions. The first is that the confirmation of, as I said before, the confirmation of the Higgs scalar discovery at the LHC was an important milestone of the LHC research program. And now LHC and particle physics enters in a new era with new possible discoveries, and for which we are in the very beginning. So this is the LHC timeline. We are here, in which LHC is preparing an upgrade to run to the nominal energy, which is starts at 13 and will go eventually to 14 TeV, which will run for about 3 years up to 2018. And then there are two possible long-term upgrades, which called high luminosity, and are was to collect much more data and to explore this machine, which works very well in its full potential. And that was this is a statement from the European Strategy of Particle Physics that has been met and made some conclusions relatively recently, that Europe's top priority should be the full exploitation of the potential of the LHC, including the high luminosity upgrade, which could run up to about 2030. On the other hand, there are future plans to explore the energy frontier of the multi-TeV region from 10 to 100 TeV. And there is, for instance, the ILC project, which is a linear collider of E plus E minus, discussed possibly in Japan. And another is the future of LHC and in general at CERN, where various options for high energy machines are discussed. For instance, this is the present status of the tunnels. Okay, so this is the SPS is the experiment proton and diproton, which discovered the mediators of weak interactions. This is the LHC tunnel. So one possibility that people discussed is to replace the LHC LHC magnets by most powerful magnets, so that the energy could increase, over double to 33 TeV. Another possibility that is discussed is to build a new tunnel which goes about 100 kilometers using not much more powerful magnets, but just of the same type that are used, or a bit more powerful that are used at LHC. In this tunnel, one could, of course, repeat, if you want, the story, and could put also other machines like E+C minus circular machine or electron proton machine at highest energies. And this is a possible picture of how, so this is the LHC tunnel, that's Geneva, this is Geneva Lake. So this new tunnel was supposed to go under the lake, circle this Salem, which is a small mountain, and go around this apertura. With 16 Tesla magnets, now they are about 8 Tesla, so it's about double power. With a 100 kilometers tunnel, one could reach 100 TeV center of mass. So this is what I was thinking. Thank you very much.
Thank you very much. Questions, comment?
Actual dimension scenario, the particle masses depends on the shape of actual dimensions. But if it is a gravitational theory, then one might expect the actual dimension over here and the end of the universe might be different. It might be attracted by the other dimensions. So how is there a nature scenario to make sure particles are all the same in the universe, like electrons or the particle would be all the same, no matter it's here or from end of the universe?
Yeah, the thing is that there are two types of extra dimensions. So our universe could remain as it is, but and the extra dimensions could be empty, because simply our universe, the forces of our universe cannot propagate to the extra dimension. So they are only gravitational. Of course, you need a mechanism that stabilizes, fixes the sizes of the various dimensions. So people have proposed such mechanism of fixing their sizes. Essentially, the problem of fixing the sizes of extra dimensions is the analog of the problem of breaking supersymmetry in the case of supersymmetric theory. Because precisely breaking supersymmetry fixes the scale of supersymmetry, therefore determines the hierarchy. Here, the extra dimensions, the size of extra dimensions is precisely where you hide the problem of hierarchy. So you need to fix the mechanism to fix the size.
Okay.
In the light of new understanding of physics, how would you describe the term vacuum? What does vacuum mean to you?
Well, the vacuum has the same meaning as in quantum mechanics. So I'm not sure what you meant by question.
Well, but if there's, you have dark energy all around.
Yeah, okay, dark energy. It's true. I mean, I didn't discuss dark energy. One possibility for dark energy could be just a cosmological constant, which means that space-time is not flat, but it is approximately de Sitter space, which is the solution to the vacuum Einstein equations with a cosmological constant.
But for example, if there's dispersion of light.
Yeah, then the cosmological constant is this can be parameterized as a fluid, which has equation of state P equal minus rho. The pressure equal to minus density, and they both constant, given by the cosmological constant. So that would be. I mean. In my talk, I didn't address the cosmological constant problem. So I didn't address the vacuum energy problem. So I addressed both the concept of extra dimensions or supersymmetry or other ideas was more motivated by particle physics. Also trying to find candidates for dark matter, but I didn't address the cosmological constant.
Okay, thank you.
More questions? Actually, because of limited time, you skipped the several slides for the experiment of the extra dimension. Can you just show them just one slide?
Yeah. So, here of these are so these are the experiments that started to be performed at shorter distances, but are sensitive to forces which are stronger than gravity. So this is the wavelength relative to the force. So this is an experiment at Stanford that improved the bounds in the range of a few micrometers in that range. So you see gravity is here, 10 to the 0. So this is the region that is sensitive to this experiment. And it is also air-to type. Simply they used much more powerful modern technology, which is based on cantilever resonances. So there is always the concept is the same, that there is a source and test particles that are attractive and try to measure the gravitational attraction. Then these are even at shorter distances in the region of nanometer range, which are experiments that are based on the Casimir effect. So yeah, this is Stanford, and this is the experiments of the Casimir force. And again, they are based on a plate and a sphere that are attracted from the measure of the Casimir energy. And finally, there are even at the shorter distances, a picometer from nanometer to picometer, using neutron scattering. And in particular, there is an experiment in Grenoble that uses cold neutrons, and they measure for instance, they measure the quantum states of neutrons in the presence of gravitational potential, and they have a plan to use these measurements in order to put bounds at new forces at short distances, because in that case, of course,
Thanks a lot. So let's thank the speaker again. Yeah. Thanks a lot. Again, the second talk is in the cancel, so you can all. Thanks a lot.
宣布说今天有哪个同学刚刚今天有来的到前面打了勾，对，后面的第二栏打勾。
第二场 talk 取消了。
不用，第一场就不用选，直接在第二栏打勾。